going to talk about one pretty narrow analysis module, but I think it's pretty handy and pretty interesting, and you can do a lot with it. This is in a larger package of analysis modules that are basically narrower applications of YT's very broad capabilities. And you should have a look on the documentation in the analysis modules to see what all's in there, just to see if there's things that exist that can help you do what you want to do. Okay, but I'm going to talk about clump finding. So clump finding, I'm going to talk about in the context of sort of if you're studying, say, star formation, and you want to know when a star-forming cloud fragments. You want to be able to identify those fragments and calculate things like their mass, their gene's mass, or various other things. So this is the sort of clump finding that I'm talking about. But I hope that as we go through this, it becomes apparent to you that it can be applied to a number of other scenarios. So in this definition, clump finding works by taking contours, isocontours, and at multiple levels, and we'll go through how that algorithm works. But a clump is sort of defined as the largest disconnected contour that satisfies various criteria, like being gravitationally bound. Okay, and that will make more sense in a second when we walk through how the clump finder actually works. So here's now I need to zoom out. Here's a nice little demonstration of how it actually goes. Oh, there we go. That's cool. All right. So imagine we're in sort of a one-dimensional simulation, and along the bottom is the spatial dimension, and this is the density. And so I have some data object that is, that is this thing with, various peaks and valleys in it, and I want to identify all the clumps in here. Okay, and so what we do is we start by basically carving out this data object. Maybe it's a disk or a sphere, or who knows what it is. Clearly it's neither of those here. And then we define the minimum and the maximum, and then we start stepping up in our contours. So this would be one contour that contains everything. And then we start stepping up the min while keeping the max constant. And so still, we have only one contour. If we step up one level, we step up another, and we still have one contour. But then we step up again, and now things start to break off into separate pieces. Okay? And then, now that we have multiple children clumps inside of this big master here, we're now going to recursively follow each one of these. So we'll start with the one on the left, and we don't need to go up any higher with the contour because that one higher contour would be over the maximum density in this thing. And so then we start to step back down, and we apply in this very specific example, we're going to say we only want to keep clumps that are by themselves gravitationally bound. Okay, so we check that this is bound, and for some reason it's not. So we throw it out. It's nothing. So then we go on back to the main, and we move that up a bit, and now we have some other ones. Okay? And so now we go with this one, and it's a single child on top of this larger object. And so we'll step back down, and then that will be the whole thing, not just that little tip at the top. And now we'll check and see if that's bound. And yes, it is. So that's one. We got one. And then we'll step up the rest and go there and say, okay, is that bound? No, it's not bound. What about the next one? No, that's not bound either. So let's step back down to that larger object. Yes, that is bound. So we will call that one thing together, we'll call that one clump. Okay? And then we'll do the last one. We'll go up to the top, check that. It's a single child, still a single child, so we'll keep extending back down. We're trying to find it. If you remember, we're trying to find the largest contour, the largest disconnected contour. So we'll go all the way down to there, and then we'll say, is that bound? Yes, it is. And so in the end, all the blue ones are the ones we keep, and the red one was thrown out. Okay? So now, okay, there we go. All right, so now we're going to, for the rest of this, we're going to actually do some clump finding on the isolated galaxy data set, because it looks like it might be right for finding clumps and stuff like that. So here is the projection of the disk along the side. This is 15 kiloparsecs in width. There it is from the top. So let's see what clumps we can sort of find in here. Okay. So does everyone have the scripts for this? If you don't, you can go to the YT Workshop website, and you can go down to my talk in day 3, and you can click on the link and download them all, and we can sort of run them together, and they will work on the isolated galaxy data set. Okay, so here's our first clump finding script. So first we simply load in the data set, and then we select the field that we're going to contour over, and this is where it should start to you should start to realize that maybe we could do other things with this other than actually being just a clump finder in this way, but we're gonna contour over density, okay? And then we need to decide what is the spacing of the contour steps that we take. And so we'll use 2. So every next contour, as we bring up the minimum value, will be a factor of 2 higher than the last. And you can experiment with that, and you can see what happens when you make it bigger or smaller, for example, okay? And then what we do after that is we say, well, we have that whole box, but we don't really care about all that stuff on the outside. We really just want to look in the disk. So I've defined myself a disk right at the center, exactly, pretty much aligned with the object that we saw in the projection. It's 8 kiloparsecs in radius, and it's 1 kiloparsec in height. So then I'm setting manually my minimum and maximum to start my contours, and I'm just setting at the nearest power of 10 for in density, just using the actual min and max in that disk. Okay, and then I'm setting a function. I'm gonna skip over this part with the function for now, but basically what I'm doing is I'm going to say we would like to keep clumps. Instead of thinking of them as gravitationally bound, we'll go with something simpler and say we'd like to keep everything that has at least 20 cells. And I'm really doing that for now because this data set is actually pretty small and simple, and if you do it with gravitational boundness, you actually don't get that many clumps, just because it's a pretty simple data set. So I am selecting for now. I'm going to say I'm going to keep all clumps that are greater than 20 cells in size. Okay? And then we start by creating one clump object, which is that whole disk that we started with here. We're saying master clump equals, and we create this clump object. We give it this data source, which is the disk. None is nothing you need to worry about. That's if it has a parent, and it doesn't have a parent. The field that we're going to find clumps over, and this function that's going to help us determine which clumps are valid and which clumps are not. Okay, and then with that, we're going to actually just call this find clumps function with all these things, all these various variables that we got in there. And let's see what happens when we do that. I'm going to run it here. Okay, and you guys can run it as well. Okay. Okay. Oh yeah, that's an excellent question. Unfortunately, at this time, the clump finder does not run in parallel. And the reason it doesn't run in parallel is because we are lacking a parallel contouring algorithm. So if anyone has one, give it to us so we don't have to turn you upside down and shake you and have it fall out of your pockets. Okay, so here we go. We're basically going through this, calling the contour at different levels, and then as things break off into pieces, we're going to chase those all down. It just all looks like this. There's a lot of spinny wheel action, which I find very easy to watch and just, zone out, So let's take a moment to do that. In what sense? Yeah. Well, you see, you have the spinny bars, and they go from left to right. Yeah. There you go. Okay, so you can see we're looking at, we investigated 34 children, 6 of them survived, in that set. Okay, and it's done. So it ran some stuff. So now the end of that script that that I showed, we write out some information. So down here at the bottom, we actually have two. One fell off the screen. We do a couple write calls, and we write out the clumps to get some information on them. For some reason, when this was originally designed, we thought it would be a good idea to open your file yourself and pass the file handle in. In retrospect, that seems pretty silly. So I would expect that to change. I think in the near future, you will just supply a file name that, sometimes you just do things in retrospect, you have no idea why you did them. So I think this is a great example of that. But let's have a look at these files and see what's in them. Okay, so, oh yeah, that's our spinny wheel output. Right, so here is the first one. This was from write clump hierarchy. And unfortunately, so if you run this, please have a look at yours. The one thing that is missing from these slides is some tabs. So what this would show if it had the tabs in there correctly is sort of how the parentage goes with these clumps. So if you see it says clump at level 0, and then clump at level 1. The clump at level 1 should be tabbed in 1. The clumps at level 2 should be tabbed in 2. And it should make it apparent which clumps are the parents and children of each other, give you the relation. But so you can see what we have here. We have a clump, the parent clump, the master had 100,000 cells, but that's not important. That was just the whole disk. But then we have one down here that had 100 cells. Then we had another one down that had 8,000, and that had some children of its own, one with 44, and then so on and so forth that had more, and you can have a look at them. Okay, and so this will give you the layout of the entire hierarchy of this thing. And if you want to see just the lowest level clumps, just the actual things that you would call your fragments, in the analogy to using this for star formation, you can look at the other one, which is the write clumps, and this gives you only those lowest level ones. See here, we're not paying attention to the level because the level is not a useful thing. It has nothing to do with the AMR level. It's the level in this clump hierarchy. And so here are our lowest level clumps. One with 106, one with 44, 94 cells, and here are the masses of these. This one's 8 million solar masses. This one's 17 million. Here's some genes mass. Here's some other things, the max AMR level, all sorts of information that comes out of these. Are people able to get this to run? Yeah? Okay, great. But you totally could, and I will show you how to do so. Yeah. Okay, so that was pretty fast with this small data set, but because it's in serial at the moment, it can take a while to run. And specifically, if you're actually doing this using gravitational boundness as a determiner of whether or not a clump is valid, it can take quite a while as you get big clumps and you have to calculate whether or not they're gravitationally bound. So this process can take a while, and we'd like to not have to run it every time we want to analyze what was the result of this calculation. And so as Stephen mentioned in his talk just before this, we can use pf.h.saveObject to store these objects. And you may ask, well, why can't I just write this out? Well, because this is not just one set block grid. This is a tangled mess of objects with children and parents and relations to each other. So we'd like to smash it into something. We pickle it, and then just write out that smash thing and be able to reverse that process. Okay. So here's an example of that. This is the exact same script. I just took the comments out so it will fit. We call the find clumps, and then down here at the bottom we have the master clump. So the result of finding clumps just adds all the children to the master clump. It puts all the parentage, all the lineage inside the master clump, and so that thing just gets all this extra information. So all we have to do is save the master clump object. I do pf.h.saveObject with the master clump, and this is what I'm going to call it when I want to get it back later. Okay. Now, once I've saved it, we don't have to redo any of that stuff. We can use pf.h.loadObject just to bring it back. And it's just like we did all that stuff. So here's an example of that. You can see you should have access to all of these scripts. Okay, and so we do have to load in the PF. That's the first thing. But then once we do that, I can simply say master clump equals pf.h.load object. We call it by the same name, and we get it back in the exact same way. Okay, so this was already mentioned, but we'll go over it again. Clump objects are data containers for the most part, but what they lack is right now an ability to retrieve the particles that are contained within them. Okay, so just to give you an idea of what it looks like, you can start with the load script. Well, you can just use this clumps as data containers script. We reload our object, and then we can look at things like the temperature in the master clump, just as the way we did with spheres, regions, any of that stuff. But then we can also look at, so now all the clumps have a children attribute associated with them. So you can do master clump.children. Now you do ling of master clump.children will give me the link of the list. There'll be a list of children associated with it. And then we can print them out and see what they are. And then the children themselves are also just data objects. And so then I can take the first child and see all the density values there. So it'll just look like that. So here we go. We have the temperatures of the master clump. Master clump has two children. Here they are. Here's a list. It's just one object and a second object. And here's the density of that first child. Okay. Does that all make sense? Yeah? Okay. So now we can go through how we could change what determines what's a clump and what's not. You know, I alluded to in the beginning using gravitational boundness, but in this example, I used just the minimum number of cells to keep it simpler. Okay, but you can change it to basically anything you want, and you can experiment with, well, basically how it changes the results. I think they call that science. So before we get into exactly how it works, I'll just say that, well, how it works is it uses a string. If you didn't notice that, we supply the actual function keyword as a string, and that string is evaluated with an eval statement. And so here's just an idea of how that works. I can set a string, and that string can be y greater than 5, right? And y doesn't yet exist as a variable in this string, and so that means nothing right now. But I can wait until a later time until that statement has context. So for example, then right below that, then I set y equal to 4. All right, and then I can say, is y greater than 5? Well, the answer is no. So, but we can do that here, and that is done with the eval statement. And so you can see down here, y greater than 5 is false, right? And then I can set it to 6, and then try it again, and you can get true. And you can try this with basically any string, as long as when that string is basically turned into actual, code, it gives you something meaningful. But that's a handy little trick, and you can do a lot of stuff with that. So this is in essence how we are determining what is a clump and is not. So here are some examples of validity functions that you might want to use. So the first one is actually just the default in this, and you notice that what we're using here is self.data. Okay, and that's just because that's how the clump will identify itself when this is running. So everything has to be self.data. So then what are we doing here? In the first one, we're actually using a derived quantity. So self.data.quantities is whatever that object's derived quantities are. And we're using a quantity called isBound, which calculates the ratio of the gravitational potential to the kinetic energy. Okay, and so if it's greater than 1, it's bound. All right, and that's exactly what this statement is, right? So if we look at it, this whole first part here is just calculating that ratio with that derived quantity, and then we're just saying, is it greater than 1? So if this is bound, this will return a number greater than 1, and this statement will be avowed to be true. Okay? We can do other things. This is the one that we use. So this is just saying, what is the size of this self.data density? That just tells me the number of cells in this. And if it's greater than 20, that's good enough for me. That'll be a clump. If I want to do, say, a minimum mass, you do something like this, self.data cell mass m sun dot sum. If it's greater than, say, 10 solar masses, that's a clump. Sure. We can do anything, right? We do, what do we got here? Oh yeah, this is if there is cells that are at least some threshold density, right? So that's what that dot any is. This statement in here would be like a Boolean array. It would give you trues and falses, depending on whether or not there are cells in here with number densities greater than 10 to the 6. And dot any just returns true if there are any true cells in there, right? Just like this, there is actually a dot all as well. So if you want to check that all satisfy the requirement, you can do something like that. And of course, what you could also do is if you wanted to just include every little disconnected contour as a clump, you could just set function equal to true in quotes. And that string of true in quotes will be avowed to true. It's that simple. Do you have a question, Devin? Yeah. Oh, that's a great question. So Devin asks where the clump object is getting saved. And that's a great question. And the answer is it's something that we haven't quite spoken of much. And that is with ENSO data sets. You remember ENSO data sets are these directories. You go in there, if your data set is, say, DD0046, after you've run YT, you should see in there a file called dd0046.yt. And that's an HDF5 file that saves a lot of things. If you've ever noticed, if you do a projection once, you see the little spinny wheels and it takes a while. But then if you do it again later, it's just done like that. That's because the projection has been saved in this .yt file. And that is exactly where the clump object has been saved. It's in there, and it's in there in /objects. So you can actually do h5ls on the YT file. You could do h5ls/objects. Yeah. Oh, it's broken. Oh, that's too bad. Okay. It was working for me as of this morning, but I did not update to the updates of the last couple of days. Okay. Well, we'll have a look at that and fix that. But ideally, that should work. This is something that is not supported right now with a Flash data set, for example, because a Flash data set is one single HDF5 file. And so it wasn't really... Oh, okay.
So H5i changes their API 3-4 times a day. And we try to keep up with it, but what I think is going on is that the way that they have changed, the way that they now access strings, which is how we store our data, may have changed. We will have to work around H5i's update.
Yeah. Okay. Well, yeah. Sorry about that. We'll get back to that. And we'll get that settled. Okay. So is this clear? Like how you would do this with these strings? Yeah. Okay. Cool. Let's go on. So one nice thing that you can do is once you have your clumps, you can visualize them with a plot collection callback onto a plot that you've made. So if you remember, I made that plot of the disk face on. Well, we're going to take that same plot, and now we're going to add the little lines around where the clumps are. And so the first thing we need to do is this callback will only operate on a one-dimensional list of clumps. And that actually gives you some flexibility to decide which clumps you'd like to show and not all of them. And if you remember, this is structured in sort of a recursive way. So you have master_clump.children, and that's a list. If you did the first one in that, it would have a .children and so on and so forth down the line. And so it can't deal with that object. But if we want to, for example, just view all of those lowest level actual clumps, those star forming fragments, what we can do is we can use this command here called get lowest clumps. And that will return to us a list of just those lowest ones, just those fragments. Okay? So then, all we do is we do the projection just as normal, as we did before. Add projection, and then set the width. I'll set it to 15 kiloparsecs, which gives us that size that I showed earlier. And then, on that plot, that first plot that we made, we will use the clumps modifier. So plots.modify clumps, and then we will give it this list of clumps, this all clumps. And then we'll just save it. Okay? And it should look like that. All right? So these are the clumps that we found. You know, clearly this isn't a great example of how well this works, but that I think is just a testament to the small size of this data set. But yeah, so here are our clumps in here, and the different colors are just what happens, you know, for example, in Matplotlib, when you plot different lines, they automatically change the color of the next line plotted, but you could certainly make them all the same color if you wanted. We'd get into that another time if you want. But yeah, so there we are. There are our clumps. Okay. So now, someone asked, well, what about all the other stuff I want to know associated with my clumps? Well, that's pretty easy to add items to that list. So the clump object has associated with it a list of sort of what I would call info items that are things that when it does those printouts will print out those various things. So the total mass, the genes mass, the minimum and maximum densities, all these things are just items in this list. So it says whenever you print any clump, print all of these things. Okay? And so we can use this add info item method to add more things. And this is done in actually a very similar way as the validity function is. It's done with strings that are evaled, and we give, in this add info item, we give two things. We give the thing that we want to print as a string that will be evaled. So for example, here we have everything just as we did before. We loaded in the object. I called clear clump info to empty out the information list. So we'll just re-add things manually so we can see how it goes. Okay, and so in this first one, we're just going to add the number of cells. And so it would be self.data, and then I've chosen cell mass. It doesn't matter because we're using dot size. We just want the number of cells. And then the second argument is a string that will be the format for how it's printed out. I understand it's a little bit obtuse, but I think if you stare at the examples long enough, it will make sense as to how you would add more. Okay, so that's for the number of cells. You can see here the mass and solar masses, self.data, cell mass msum.sum. Notice the sort of clever placement of quotes. That's to make sure that that whole thing remains a string. Right? I use single quotes on the outside and double quotes in the middle. You can also use a backslash quote to indicate that it's literally a quote when you need to do things like that. So here's the volume weighted genes mass. There's a couple other things, right? And we have one additional example. We have a little recipes dictionary in this source file with other more complicated examples of what you can do. And to have a look at it, you can check out the source file, analysis modules / level set / clump handling. Go down to the bottom, and we have one in there that calculates the distance from the center of mass of the clump in question to the center of mass of the main master clump. So if your master clump is a galaxy, you might want to know what's the distance from that to that. You know, you could do the same thing with what's its radius. You could do, just about anything. So you can have a look and see how that's done. And then here are a couple other examples. And so then, if we run, I just recall the right info, the right clump info. And here's that same stuff, except here in the middle, here's our distance to center of mass. So 5 kiloparsecs. This one's 3 kiloparsecs, et cetera, et cetera. Okay? And that really covers just about everything you can do sort of with the clump finder as is. I think it's clear that there are areas where it could be better. but that we would invite people to get involved in that. And that's all I have to say for now, but I'd be happy to answer more questions. Some of this stuff might not be clear, so thanks for listening. Any questions?